Welcome to the course on machine learning. In this video, we will learn about Ensemble Learning. Ensemble Learning makes use of other machine learning algorithms as components to learn a collection of predictors. It combines the output of multiple classifiers for the better accuracy. So, if we have multiple learners of same or different output, we can combine them together to get the better result. We have to generate base learners. We will call it as a group of learners. They belong to maybe of different algorithm types, having different hyperparameters, maybe different representation and different training sets. And these base learners are combined together for giving a better result. So more predictors are obviously better than the single predictor, and the predictor can be of same type or different type. For example, we can combine support vector machine, a neural network model, or a decision tree, a nearest neighbor model together. The weighted average of the output of the individual predictors is considered and the final output is calculated. You may have seen a TV show called as Kaun Banega Karodpati. In that, there are two lifelines. One is a phone a friend and audience phone. So let us take this example. If you got stuck in one of the questions, then what will you do? Will you call a friend or you take an audience poll? So if you think of calling a friend, then your friend will give you a result, but here a group of people will give you a result. So that is what is the basic difference between a single predictor and a group of predictors. So different learners may be good at different part of the data, so that will help us to convert a weak learner to good learner. Let us take this example. So for example, let's say we have decision tree algorithm, a support vector machine and a logistic regression, and we have some data set where we have features and labels. So think about that. Decision tree algorithm gives you 65% accuracy, support vector machine is giving you 75% of the accuracy, logistic regression gives you 60%. Then we can combine the output of all those three models and we can have kind of voting system. The majority vote can be considered and then we can think about the final output. So let us say this for this particular test image of hot dog. So decision tree predict it as a hot dog, support vector machine predict it as a hot dog, and logistic regression predict it as not a hot dog. But when we combine together, so majority vote is hot dog, so ultimately the final output is a hot dog. And that is what is the power of combining multiple predictors. Now let us have this comparison with the bias and bias and variance. So bias is the measure of flexibility. So if the model is flexible, then bias is low. For example, decision tree. And if the model is not flexible, then the bias is very high. For example, linear regression, as we have seen in the past lectures. Variance is high when you have different subset of data set, and variance is low for the same set of data set. And in ensemble, basically we combine for low variance and high bias. So that means we will have work on the same set of data set with the not flexible model. So we combine weak learners where error is less than say 0.5 or 50%, and following condition can be required, that independent learners are there and having accuracy more than 75% or 70%. Suppose one learner gives you output, then the confidence is 0.7, but if 10 learners give you the same output, then the confidence is 1 minus 0.7 raised to 10. That is what obviously greater. So in combined output, unweighted voting or weighted voting are the choices. Weights can be assigned according to the accuracy of the model, or it can be one by variance. For example, Bayesian classifier can be the best example of this, and we can create multiple data set with multiple classifiers and combining the output of that. For example, random forest. What are the common ensemble techniques? So bagging, boosting, stacking, and random forest are the common ensemble techniques. Bagging is nothing but bootstrap aggregation, and random forest is also sometimes called as bagged decision trees. Let us see now the simple ensemble technique. So all the unweighted average or the majority votes are considered, and weighted average is the upper weight for the better prediction. For example, if y1 dash is the function of say all the input x1 x2 up to xn, y2 dash is the another function, let's say f2, on the same data set, and y is nothing but the sign of summation of alpha into yi, where alpha is the weight. So we will assign weight to each particular output, and then we will combine all those together. Now, how to train the predictors of predictors? So treat individual predictor as a single feature. So let us say the y1 dash, y2 dash, and y dash, all are considered as a single predictor, and we will train each predictor separately. So it is similar to training a multi-layer perceptron, and the special case can be there if we have binary weights. And we can train the ensemble weights FE on the validation data. So can we make weights depend on X? Yes. So weights alpha phi X indicates expertise. So we can combine average or just pick up the largest value of that, and then we can make the weight according to the input. So bagging is nothing but a classical technique to generate lots of predictors and combine them together to do better job. So why learn only one classifier when you can learn many? That is what is the basic philosophy. And committee is nothing but the learn k classifiers, average their predictors, and then you can have the final average output. So bagging is called as bootstrap aggregation. You can learn many classifiers, each with the only portion of the data, and you can combine it through averaging the values of that. The idea behind bagging is to reduce the overfitting of the data. So you can think about this particular example. So here we have decision boundary 1, decision boundary 2, and decision boundary 3. So there are 3 different classifiers, and when we combine it over here, we get all those 3 decision boundaries, and this is the final ensembled decision boundary, which will give you the better result than all those 3. Overfitting is a problem with many classifiers. So we use test data to see if we have gone too far. We can also use cross validation to avoid overfitting. In cross validation, we can split the data in training and testing data set, and each of these defines a different classifier. Typically we use this particular to check whether we have overfitted the data or not, or we could consider combine them instead to produce a better result. Bootstrap is a classical statistical technique. It creates a random subset of a data by sampling, and we can draw n dash of the n sample with the replacement. So you can take, say, n dash is the subset of n. Okay. And bagging is it repeat k times, and we can create a training set of n dash where n dash is less than n, and train the classifier on the random training set, and then get the output from that particular classifier. To test, run each trained classifier. Each classifier votes on the output, take the majority. For regression, each reprocessor products, then we can have average of those values. So this is the example of the diagram explaining the bagging. So let us say we have a data set. The data set is combined into the is divided into training data set and testing data set, and then we can have different bags. Let's say randomly select a data point or a row one by one, and into this bags repetition allowed. So we can split the data set into, let's say, size minus m, where it is less than n. We can train on each particular portion of the data set. We'll get the output, and then we combine all those output, and you can have the voting of that. So again we'll discuss about the bias versus variance. So we only see a little bit of data and we can decompose error into two parts, that is bias and variance. Bias is the error due to the model choice. So it can our model represent the true best predictor, and we can get the better result with the more complexity. And variance is nothing but the randomness due to the data size. So it will be better with more data and worse with the complexity. So this particular graph actually represent the bias versus variance. So when you have a simple model, then the predictive error is high, but as you go with the model complexity, then there is a high variance. So what are the advantages of bagging? So bagging is simple to implement and it reduces overfitting, but there are some drawbacks as well. The complexity increases with the number of partitions of the data and it does not have a leap performance. Bag decision tree or random forest. So it is another version of another method of ensemble learning. It randomly resample the data and it learns a decision tree for each resampled data. It simulates equally like dataset that we could have observed instead of their classifiers, and it averaged their collection. Hmm? And the classification technique is based on the majority vote. Back decision tree reduces memorization effect. So not every predictor sees every data point, so it lowers the complexity of overall average. Usually, it's better generalization performance. Random forest, the application of bagging using decision tree, and the problem is that with lots of data we learn the same classifier. Averaging over those doesn't help, and what is the remedy for that is to introduce extra variation in learner. At each step of training we allow only a subset of features, enforces diversity, that is the best feature that are not available, and average over those learners with the majority vote. So this is the code snippet explaining the decision tree split data set. So for each of a subset of feature and for each possible split, we calculate the score of the split, that is the information gain. And after that, we will pick up the feature and split the best score recurs on each data set. Boosting. Boosting take weak classifier and make a quite robust one. For example, Adaboost algorithm. So this is the diagram explaining the boosting technique. So with the data set can be split into training and testing, then randomly selecting point one by one into the back where the repetition is allowed. We train the model on that, we test it with the data points, and again we train it and test with the training dataset on the ensemble, and dataset that is giving the data points that are giving the wrong prediction, we will repeat this technique for again for those particular data points. So until that model learns on those data points where it had made the mistake in the previous classification, we will repeat this technique. So this diagram again gives you an idea about boosting. So in the first split there are three mistakes, then it is fed back, again the model is trained, then there are three mistakes, and it goes and goes on until it learns with the decision boundary. Okay. Gradient boosting. Boosting is a machine learning ensemble meta algorithm for reducing bias primarily and also the variance of it. It focuses on new learners on examples that other gets wrong. That it trains the learners sequentially, and the errors of early predictions are hard examples. Means you have to relearn that particular examples, and focuses later on predictions on getting these hard examples right. It combines the whole set in the end, and it converts many weak learners into complex predictors. And this is the diagram explaining the gradient boosting. So learn a regression predictor, compute the error residual, and learn to predict the residuals. So in the first example, this is what is the simple learning a simple predictor. This green dot shows you the errors, and here it learns it again, and then it combines that error into the model, and then the model again rerun and relearn on those particular mistakes. And this diagram shows you the subsequent performance of the regression. In gradient boosting algorithm, we first of all make a set of predictions. Let's say y cap of I, and the error in our prediction is j y comma y cap. So that is nothing but for mean squared error. So j is the cost function, which is nothing but the summation of all of the squared errors. So we can adjust y cap to try to reduce the error. So y cap of I is equal to y cap of I plus alpha of f of I. So where f of I is nothing but the function of j of y comma y of I is nothing but yi minus y cap of I for mean squared error. Each learner is estimating the gradient of those functions. Gradient descent takes sequences of steps to reduce j, and it's nothing but the sum of predictors weighted by step size alpha. So this is the code snippet of gradient boosting in MATLAB. So as you can see, the mean is calculated first. Then for every k value of 1 to n boost, the model is trained, alpha is set to 1, then the residual of this particular uh, given new prediction is calculated, and the test data set is again the, the predicted. In Adaboost, the main concept of Adaboost is to choose T, dummy classifier from a family H of T, and create a weighted average quotient. Each classifier will output a numerical value, the sign of which will determine the class, and its magnitude will represent the centritude of such classification. The beauty of it is that we can create quite robust classifier from very dummy, very fast one. And this is the mathematical model of the Adaboost model. So y cap of t is equal to sine of ht of x, where it is nothing but sine of summation of t less than t beta t into ht of x. The trick will be to choose which h of j dummy classifier to pick, and how to come up with the optimal weights the bit of t to combine them. And this is the algorithm of the Adaboost model. So input is x1 comma y1 up to xn comma yn, the number of iteration. We initialize the value of dn to 1 by n for all value of n, and we repeat it for 1 to t. Train the classifier with respect to the weighted sample set and obtain the hypothesis, that is nothing but h of t is equal to x plus 1 or minus 1. We calculate the weighted training error epsilon of t of hi, and then we set alpha of t to half of log 1 minus sum epsilon of t divided by epsilon of t, and then we update the weights accordingly. So dnt plus 1 is equal to dnt exponential value of minus alpha t yn ht xn divided by zt, where z is the normalized constant, such as dnt plus 1 is equal to 1. And we break if summation epsilon t is equal to 0 or epsilon t is greater than or equal to half, and the output is nothing but the summation of all those particular alpha of t divided by alpha of t, summation of alpha of t into ht of x. Thank you for watching this video. If you like this video, please press the like button and subscribe to my channel. Thank you.